All right, back with practice final problem number 4. We're going to do parts B and C right now. Um, for part B, we want to find big Y of e to the j omega, which is the Fourier transform of uh, Y of n. Now, I defined Y of n. I drew a picture of Y of n. So, and actually, let me do this. This is -2, and here's 2. Just get rid of that. And this is what it looks like. It's a pulse with a width of 4, and it starts at n equals -2 and ends at n equals 2. Now over here on the right, just as a reminder, here's the definition of the unit step in discrete time and continuous time, and notice the big difference here. The big difference here is that in discrete time we have a less than or equal to 0. When n is less than or excuse me, when n is greater than or equal to 0, the unit step evaluates to 1 in discrete time, as opposed to in continuous time. There is no less than or equal to. There's only less than and greater than. And this is because in continuous time the unit step's kind of, it's kind of rising up to 1. This would be 0 right here, and this is this is your rise time, and you have to worry about that in this class. But here's the important part: is this less than or this greater than or equal to? And so I wrote out a table here with the different values of n, and here's u of n plus 2, and then start plugging in the numbers, and you can see that this one turns on right here, right, and it stays on, and then u of n minus 3 doesn't turn on, that turns on right here, and then it stays on. And then when I subtract u of n minus 3 from u of n plus 2, what I get is that I'm on here, and I'm on here, and then I'm off the rest of the time, and I'm off that up there. So these are all off. So you can see that this is, so this would be the plot of that. Now let's define y of n as a piecewise function. It's going to be equal to 1 when the magnitude of n is less than 2, less than or equal to 2. And it's going to be 0 when the magnitude of n is greater than 2. And using table 5.2, let's just let's say that big N sub 1 is equal to 2. And using table 5.2, if you go 3/4 of the way down, you can see that what we have here matches exactly with the table. So then immediately that tells us that big Y of e to the j omega is equal to sine of omega times big N sub 1 plus 1/2 over sine of omega divided by 2. Change out our big N sub 1, we get sine of omega 2 plus 1/2 over sine of omega sub 2, or omega divided by 2, and that's equal to sine of 2 plus 1/2 is 5/2 omega over sine omega 2. And that's part B. That's as simple as part B. We already did part A, and I think I showed pretty explicitly how to apply the time shifting. So we can see here that all we've done, so z of n is equal to y of n minus 1. I've shifted everything to the right one. So here it would be z of 1 coming along just like this, same magnitude. It's just shifted once, one to the right. So that automatically tells us that big Z of e to the j omega is going to be equal to the Fourier transform of y shifting in time by 1, which is equal to e to the negative j omega times 1 y of e to the j omega, which is equal to e to the negative j omega times sine of 5/2 times omega over sine of omega over 2. And yep, that's it for parts B and C. Pretty simple. Remember this is important right here, how the discrete time unit step is different from the continuous time unit step. And if you need to, tables, always make yourself tables, it'll help. All right, thanks. I'll be back with some more videos soon.